Hi, this is Dr. S. P. Arsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration and control, we are discussing about the vibration generation mechanism, that what exactly the basic physics involved in the generation of these vibrations by various actions. And as we know that there are various components in the machine, like you see, and these components are just in the rotation or in like some other kinds of motion, and during this motion they are generating the oscillation or some kind of the excitations in the system. So, in the previous class we discussed about the self excited vibrations under the generation mechanism, and we discussed about that what exactly the cause is. Even the system is robust, even there is no defect in the system itself, but even after that there is a condition of having the excitation, and sometimes these excitations even lead the system towards instability. And we discussed all the causes of that, or what are the conditions in which we can categorize the system under self excited vibrations. And even we discussed about one of the specific term, that is negative damping. The negative damping means, you see here, as we discussed yesterday, that the feature of the damping means to extract the energy, to absorb the energy from the excitation source. But instead of that, if energy is being fed to the system, certainly it will try to make system unstable, and this unequilibrium part due to some energy supply is one of the hazardous cause for unstable and which lead the system towards the failure. So, we need to take this issue seriously, that when the system is under the self excited vibration, which always turn the system to the non homogeneous solution, we need to check it out that how we can control those things. So, today's lecture is absolutely focused on the other aspect of vibration generation mechanism, that is the flow induced. What exactly the mechanism is, because sometimes we see that along with the vibration there is a huge sound when the flow is being there from various duct or the devices. Either the flow is we can say the liquid or the air or any kind of thing, it always created a huge amount of vibration and the noise itself. So, when we are talking about the generation of these sound and vibration, and when we are trying to correlate the flow with these two aspects, then certainly we need to check it out that what exactly the effect of these sound and vibration on the surrounding feature. And if we are just taking the example of simple the jet engine, or even we can say that there are various flows through the fluid machines or any kind of thing, like the fans, pumps, compressor, the diesel engines, they are clearly showing that when the fluid is just moving, or when there is a passage of the fluid from the critical locations for the conversion of the pressure and kinetic energy, then certainly there is a huge amount of vibration from vibration generation from the source and transmitted very fastly to all across the component and the surroundings are. So, these cases which I talked about are ultimately cause the huge amount of vibration and sound generation, but these waves or these the signals which are being generated, they are absolutely categorized under the non-stationary processes. And this is one of the significant criteria when we are trying to measure those things. We need to analyze based on this non-stationary feature of the generations, irrespective of in the gases or in the liquids. So, you see here in that the basis of the analysis, as we know that they have the non-stationary type of features, then these processes which needs to be analyzed based on the acoustic sources or the vibration sources is being based on the theory given by Professor J. Lighthill in somewhere in 1950s. Lighthill theory is a flow acoustic sound or vibration radiation, basically the expansion, is absolutely based on the assumptions that there are only three basic types of sources which are being possible in the fluid, like the monopoles, dipoles and the quadrupoles. And all these sources have either in separation or in combination when they are simply expanding in terms of the radiation. As you can see on the screen, when the train is moving, the air drags are being there, they are absolutely putting the drag and the lift forces. But when we are trying to map the forces, the aerodynamic forces all across to the device, then you will find that there are, you see, like the lines where the air movement strike, and you see according to the shape of the train there is a streamline motion, but there are some kind of, we can say, the surfaces just close to the surface of the train. These areas are simply showing a kind of turbulence when the trains are moving or the vehicles are moving at the high speed, and these wake formation or the turbulences are mainly due to pressure fluctuations, and these are creating huge amount of sound, even not only on the surfaces of that, but also you see in between the two bogies where we have a gap, and these you see the kind of irregularities are being formed in the air, and they are creating the huge amount of sound or vibration due to the turbulence effect. So, these turbulent boundary layer theory in the flow field is being created due to the pressure fluctuations at the surfaces, and they are the basic cause for the vibrations or the sound when the train is passing at the high speed. Or even we can see little more inside, and we can see that the kind of, you see the surfaces or which these turbulent effects are there, you can see these are all turbulent eddies are there, you see, and they are basically even the entire fluid flow across the we can say the train or any vehicle is of the combination of the turbulent and the laminar, because somewhere you see the steady flows are being there according to the streamline conditions, but somewhere because of these pressure fluctuations in between the air and the surface interactions, these turbulent boundary layer theories, the boundary layers are being created, and we can apply this theory to formulate that how much turbulence is there according to the speed and air velocity. And these eddies are the basic cause even for creating, you see, not only the vibrations but also the transmission towards the inside of the vehicle. So, we need to check it out that how much pressure fluctuations are there through which the turbulence or the turbulence vortices are being created, and both are basically responsible for the noise not only outside but inside the vehicle. So, with this consideration, the light wheel theory is just give a proper justification about that we have the non-stationary waves on that, and this justification is based on the reformulation of the fundamental equations of fluid flow, in which we need to consider not only the equations of motion but also the continuity equation in such a way that the turbulence effect due to the pressure fluctuations, when you see this pressure energy is being converted into the velocity, then we need to consider this nonlinear impact of that. And the source terms certainly motivates exactly into three main fundamental types, as we discussed already: monopole, dipole and quadrupole part. But one of the weakness also in this theory is it always ignores the basic interaction between the fluid flow, and you see here how the sound and vibrations are being generated exactly, means it cannot give you some kind of empirical situations where the relations are being set up between these two. And sometimes we can say that there is certainly, when the fluid flow is there, the kind of exciting forces which are being generated and the impact forces are being occurred on the surfaces, they are absolutely creating the sound and vibrations. So, we cannot ignore this where the interactions is significant. So, at that time the light wheel theory is somewhat not matching to the accurate results. just like you see the visual sound, or the we can say the vibrations, when we are just using a visual feature, and this is basically being caused by the vertex shading. So, you see here sometimes we need to say that if this kind of interaction is not that significant, we can apply the light field theory to find out that how much you see the like in particular all these three types of poles, how these relations are being set up, or how we can analyze the basic physical theories with that. So, as you can see, we can straightway take all three types of sources and we can find that what exactly the physical mechanism is there in that part. So, if you see that the table clearly shows that we have the source say monopole type, then it is clear that the physical sense is saying that we have a clear fluctuations in the volume or the mass flow, because in the fluid flow the continuity equation says that the rate of inflow and rate of outflow is same, and if it is the steady state phenomena, then certainly you see we can say that the streamline flows are there and we can apply straight with the control mass to get the continuity equations. But when you have even the monopole, we need to check it out that even in that there is a sound and vibration creations. So, we need to understand the basic physical system and we need to check it out what exactly the fluctuations are there in the mass flow or in the entire volume, because there are situations in that in which the cavitations or inlet outlet piston part or inlet outlet walls, or even you see here when there are some different cross section of the pipes and abrupt changes are there, certainly there is a clear situations where we have the sound and vibrations generations. The second is the dipole, in which it is a clear fluctuations of the forces. So, these forces, even we can say some exertion part is there through propeller or the fans or any kind of you see like the external source, they can clearly interact these forces, drag forces, or you see the exciting forces clearly interact with the surfaces and induce vibrations or the soundeds. And the quadrupole is something in which you see here it is a clear not only the force, but the moment, couple, or any kind of the combination of, means we cannot say that you see only the force which is being like the responsible figure, but the force when it is being applied through the line of action, or if it is being applied at certain distance, can create the couple, and even you see here this couple is also responsible for having the huge sound or vibration generation. Just like the basic example is the jet flow. In jet flow we know that there is a significant amount of the noise or vibration because of the free turbulence, and this free turbulence is not coming only because of the force, but it is coming because of the various force directions and the couples together. So, there is you see the coupling of the various types of forces together. So, all three types, the monopole, dipole and quadrupole, are basically responsible for having a vibration and the sound in which you see the various conditions are there. So, in order to find out the sound and vibration generation and how you see like these things are being generated, a certain type of source is being there, and all the flow conditions or you see like the situations which are being there is absolutely depends on these boundary conditions, operating conditions, and the scaling laws can straightway used for that to analyze the system. So, scaling law can be used to determine how much increase is there in the vibration power or the sound, and how it can be obtained due to the change when you see like say the velocity is increased, the pressure is dropped, or any external source is being added, through that you see some forces are being added. So, how we can use these things, or else we can say that the another use is to be able to rank the relative significance of these three types, because we know that when the things are being changing, what exactly the relation in between that and what exactly the significance of these on the propagation of that. So, you see like this theory is giving us the domains or which we can find out the dominant effect of these features. So, what is the scaling law? So, we can use you see the equations that can straightway compare the power generated in the free field in between the dipole, monopole, or even the quadrupole and dipole, that how much you see the power generations are there when these transformations are there. And these equations basically can also be termed by he, and it is you see like the Professor He, the Chinese scientist who simply gave set up these relations. So, we can see that the power ratio between the dipole and the monopole is nothing but equals to proportionate kd square, where k is the wave number and d is the length, whatever the scale length is there, which simply indicates that what is the size of the source region is. So, that is for the small, we can say the source region, this theory is absolutely valid, because whatever the ratio is there, whatever the proportions are there in between the transformation is absolutely depending on how much distance and the wave numbers are and the square term. Even similar theories can be set up for the ratio, the power ratio of quadrupole to the dipole, and it is also giving, because there is a straight one phase difference, it is giving kd square, where we discuss that k and d. So, you see when we are applying these things for the flow acoustics, you see whatever the acoustic radiations are being coming through the system, we can say that it can be straightway determined whether or the source region is acoustically small or what. We can straightway say that it is absolutely depending on the two main feature, the wave number, that you see what exactly like how many waves are being coming out in a rapid way, and the transmission feature, and then the second is what is the region where you see these free expansions are there. So, for flow generated these vibrations and the sound, a rule can be straightway like put, and the validity of this is absolutely based on the frequency spectrum, because we need to ultimately find out what exactly the proportion limit is. And for that you see we need to find out you see what exactly the frequency components are being associated with the typical flow velocity and the sizes, because ultimately all these powers are being generated based on the flow velocity. So, we can relate this frequency, say this frequency is nothing but the scale frequency Fst is nothing but equals to the flow velocity divided by the size where the free expansions are there in the source region u by d. And this characteristic frequency, which is a dedicated frequency for the flow generated vibration, is usually called the Strouhal frequency. So, we can say that we can straightway find out that how much frequencies are being generated, we can either correlate that how much velocity is there in the flow field region, or else you see here what is the flow field region and the velocity is there, corresponding dedicated frequencies are being generated in this. So, now you see here we are going to consider the various cases in that, and we are going the three cases, and in that you see we are trying to analyze that how you see these frequency and the regions are there. So, in the first case which I am going to show you, we have the flow about the cylindrical barrier, and around the barrier we have clear periodic vertex features are there, and through that the shading is begins at the very small number, even we can say the Reynolds number, where the flow is pretty okay along the diameter of this cylinder. And this shading effect is simply giving the fluctuation in the forces, and you see here through that the dipole sources can be related in this. So, in anyway this equation is just showing you see that how the cylindrical poles are being there, how the air streams are being like crossing to this one is creating the huge amount of sound and noise and spreading in faster way. So, we can by putting some extension at the right region, the exit region of the cylindrical pole can reduce the kind of you see the sound and vibrations generation because of the streamline sections being provided, or else even we can just put the small turbulence regions, you see the generators through that you see here when the small energy is being interacted with this, there is a interaction in between the flow path and a clear variation is there in this. So, even in these cases whatever the vibration or the sound is generated is basically, as we already told, that it is the Strouhal or Aeolian tones are there, and we need to check it out that what exactly the shading effect is there, which can straightway relate towards the dipole feature. So, we are also going to discuss about the second case in this, that is nothing but you see a jet phenomena in which the non-pulsating turbulences are being there, and in the flow when they are just passing through the duct, they can straightway create the quadrupole features because of the disturbance in the jet flow sources. And this Strohal frequency can straightway obtained using the jet flow velocity and the diameter of the duct. And we know that since it is a clear quadrupole feature, so a broadband frequency spectrums are being obtained, which we need to find out that how we can simply feature out in the scaling part. Now also you see in the third case which we are going to discuss about, the propeller. Propeller is rotating, means some extra features are being added to the system, then we have a clear rotational frequency as the propeller rotating at that frequency, and the blades of the propeller can immediately generate a time varying forces, and they are the responsible feature for creating a huge amount of vibration. So here it is, you see we have all three types of cases, right from a proper periodic vertex shading to the propeller action. And you can see that when a periodic vertex shadings are there, there is a, you see the u velocity which is all along the streamline, and when they are passing through the cylindrical barrier, then we have some kind of wave formation, and whatever the excitations are coming, they are absolutely a well featured excitations. It is a dipole excitation, and we can get this vertex shading frequencies just equals to 0.2 times of u by d, because ultimately we are assuming that this much conversions are being there to excite the system. In the second flow, where a quadrupole features are there in turbulent jet, you can see that in this particular jet diameter, the flow velocities are being there, and they are creating a huge amount of vertex formations. And in the excitation, it is very much clear that how much you see the exciting features are being there according to this alpha and FST. And the third case, where we have a known input frequency F0, which is nothing but the rotational frequency, and with the number of blade k, we can get the harmonics of the exciting frequency FST, which is u by d, and you can see that this when this u, the velocity is interacted with the blades, then we have a clear interaction, and these interactions are clearly shown there, that how many number of blades are there, correspondingly the frequencies are being there, and these are all the harmonics in that. So these three cases are clearly showing that how the interactions are there and how we can feature out based on the monopole, this dipole and the quadrupole. And in that also you see, if we are saying that the angle is being divided by the frequency 2 omega f0, then we can straightway get the kind of frequency, because you see when we need to divide with the number of blades, then the frequency which is coming out is nothing but the blade passes frequency. And this is something we can say the natural frequency of the system according to the blade design and the number of blade at which you see the excitations are coming without any defect. So blade passes frequency is, we can say, the characteristic frequency for such kind of systems, and we can say rather it is a fundamental frequency. And when you see the vibration of the sound which is coming out due to the through the propeller, it consists of a periodic part, means there are various harmonic features are there, so like the multiple excitations are there according to the harmonics of blade passes frequency. And also we have the broadband, and this broadband is basically showing the turbulence effect existed in these flow motion, and because of that the huge amount of amplitudes are being created. So for a periodic part, the squirrel frequency corresponding which is corresponding to the blade passes frequency, we can simply find out that you see how much these peripheral velocity and we can say the diameter is there, correspondingly we can get that, and which is clearly showing that according to the radius of propeller, the frequencies are being like varying, and we can get this by 2 pi a divided by k, where the k is the number of blades. So if we are just putting those things in the He number, then we can find that the He number is nothing but equals to the Kd or 2 pi f0, the f0 is the rotational frequency, into the d diameter divided by c, or else even we can say that this is nothing but equals to the 2 pi m, where m which is a very common phenomena, is the Mach number U by C, and we can say that the flow is simply like from the acoustic source. If it is small, we have a small Mach number. We can categorize the flow velocity with the sonic, subsonic, supersonic part with these comparison of the flow velocity and the C. And with this, you see the Mach numbers, even we can now adopt this into our His formulations. So it is nothing but equals to when the power dissipation or the power ratios are there in between the dipole and the monopole, it is proportional to the m square, or even for the quadrupole and dipole, it is also proportional to the m square. And for small values of Mach number, the monopole is the most effective flow acoustic source. And after that, there are, you see, the dipole and the monopoles are having the less effect in the radiator feature or in the radiation feature, and the propagations are there in the sound. So that's what it is, you see here. When we are just treating the system in the subsonic flow, we need to take care whether the system is like the monopole, then we can say that it has maximum impact for the flow acoustic source. So this is what you see, one of the conclusion for this light wheel theory with this He number, that how the things are being there. So besides the ranking from the monopole to dipole to quadrupole for such systems in which you see the small Mach numbers are there, we also need to see, it is one of the interesting figure, that how the radiations of each source type is depending on the state of fluid. Because the fluid is sometimes, you see, like when they are passing, sometimes it is changing its state. So we can use again the same scaling law through which we can describe that how you see the such such sources are being depending on the phases of the state of the fluid. So if you are taking first the monopole, then we can apply, you see, the equation straight away to monopole. Say the monopole power source is Wm, then Wm is proportional to the density rho 0 Ck square Q0 square. The Q0 square is basically the volume, like the discharge part to the volume, that how you see the variations are there in that. And the density is also one of the important figure here, that how the variations are there in this. So if you are considering this volume flow Q in the scale feature, then we know that it is nothing but equals to UD square. And when we are keeping this into our main formula of our monopole power, then Wm is nothing but equals to rho 0 C Kd square, as we know that the Kd square is straight away coming with the wave number and the distance in which the fluid flow propagation is there, into U square d square. Even we can simply put the wave number k, which is nothing but equals to 2 pi f st divided by c, or else we can say that it is 2 pi u by cd if we are just replacing this fc by that. So ultimately we have the power in the monopole, whatever the power generations are there through the monopole source, is proportional to rho 0 d square u4 by c. So you see that this monopole source, how it is depending on the velocity. It is the fourth order of velocity, so it is highly sensitive to that. And even if we are just putting this equation for dipole, then you can see that it is rho 0 d square u to the power 6, but divided by c cube. So now you see this u6 by c cube is now just reducing the intensity of these phenomena. And even if we are just trying to apply this concept to quadrupole, then we have the wq is proportional to rho 0 d square u to the power 8 divided by c5. The means are pretty simple, that you see here, when we are just trying to go from monopole to dipole, dipole to quadrupole, the variations in the velocity and in the velocity, the fluid flow velocity and the sound velocity is significant there, and we are absolutely putting the c, c cube and c5 when we are just trying to approach from monopole to dipole, dipole to quadrupole. So we can see the variations of such parameters and the effect of these parameters on the wave generations, or we can say the vibration generation. So, the equations which we just showed there, you see, just describe that how the motions are there in the fluid flow and how we can characterize the fluid flow motion with the flow velocity u, which can be converted into the vibrations. So, if we are just talking in the physical sense, that means that the scaling law clearly describes that how the kinetic energy in the fluid flow is converted into the excitation energy, or how this energy is being used for creating the excitation features in the system in the monopole, quadrupole and the dipoles. So, for the cases in which you see there are some other energy sources in the fluid flow, like the thermal like energies are there through various sources, like due to combustion or due to various other features, then we need to incorporate these features in the scaling law, which makes somewhat more complex scaling laws are. Because right now only we are looking towards the flow velocity and the sound velocity, and we are just trying to compare like these things to characterize the fluid motion and to understand the basic physical mean of the vibration generations. And whatever the equation which we shown, like like for quadra, for the dipole and for monopole power generation, is called the light wheel U10 law. That means you see here in this, it is clearly showing that how in the light wheel theories, how the fluid velocity is creating the vibrations or the same time the sound in the system when the fluid flows are there. We can see that the variation of a clear sound level, that how much sound level are being created when the fluid velocities are there through the jet. So, in that the velocity dependence on this vibration and the sound generation is absolutely depending on the two main features, how much waves are generated, and you see here what is the fluid velocity. So, as we are just going with the model source, you can see that it is absolutely depending on the U8, that was you see for quadrupole, and then how the variations are there. You can clearly see that these dotted lines which are clearly showing the model curves in that, which are being recorded by the Chobotov and the Powell in 1997, in which you see here the sound and power is absolutely connected to the size of the jet diameter of the source, and also it is depending on the wave generation, that how many wave generations are there. So, you can see like this is what it is, and when we are going towards the jet engines, it is a clear you see here like the things are being very rapid when the high velocities are there, and accordingly you see the sound generation is very large, which can be computed based on 20 log t. And when we are going towards even the rockets, we know that the flow velocity is quite significant here. This is the third portion, and there you see here the sound generation is very significant, even the flow variation is just in the cubic form of the velocity. So, what the means are that you see the variation and the sound velocity are the two significant criteria to generate the sound or the vibrations in the structure when they are just going in the common model source or the jet engines or the rockets itself. So, you see here we can say that the exponent of velocity is absolutely like showing the dependence of the fall off of the sound and vibrations power related to these features, and whatever the sound level which is being or the vibration level is being generated is absolutely depending on these exponent. So, when you are just going for a high level of thrust velocity, we have the proportional features in the rocket or even the jet engines is u cube. And we can say that if we are just going back to the basic theory, that if the kinetic energy is the main energy reserve for this vibration or the sound generation, then the available energy per unit volume for any kind of jet is W0 u square by 2, because we know that when we are just trying to apply this theory, then this is just giving the available power. So, that means you see the available power which corresponds to the outflow of this much kinetic energy per unit area. If we are just trying to see that, then every time there is an increment of the kinetic energy as W0 u cube by 2, because we know that when we are trying for the jet flow, every time there is an increase in the velocity in the proportion of u cube only. And the basic energy is W0, which is, you see, the initial power, u square by 2, and when we are just going beyond that, then it is always been expansion in the increment of u0 W0 u cube by 2. And this is what my kinetic energy with whatever you see, like the mass per unit area is W0 is, like putting in that way. You can see that the kind of effect of turbulence, and when you are just trying to see the gradient of the velocity as it is just passing through the long tube. So, we can see this is what my air streams are, and when they are just passing, the clear interaction of these molecules are creating the turbulence effect there itself, and we have the two mixed region. The closed area is just showing the less intensity of the turbulence, and you see here after certain area of the free expanse, we have the huge effect of this turbulence feature, and with that you see the maximum noise or the sounds or the vibrations are being generated there. But as we put any small, we can say, the obstruction in between that, then even you see here in the air stream, in the second figure you see here, the turbulence effect starts from here, and which creates the huge turbulent effect at the just exit part of the pipe or the duct is. So, you can see that even at the beginning we have a huge mixed region, and this mixed region is just showing a turbulence effect on that. So, the mean is that you see, even if we have any obstruction, through that the irregularities are being generated, and with these irregularities the turbulence effect is quite significant in those part. So, we know that when we are just going towards the three dimensional features of that and we want to apply the scaling law, we need to put certain assumptions that the vibration field and the free field conditions are always be along the flow path even in the 3D way. And in practice sometimes we are saying that the source region is often, you see, like in the enclosed feature, just give a throat to the duct with the flow, so that the variation is there in the pressure energy to kinetic energy will be along the streamline, not like any obstruction by we are putting and creating the turbulence part. And if an analysis corresponds to the cases like 1D or 2D sound, or we can say the vibration field, then we need to check it out that how we can analyze with any kind of arbitrary dimension. So, you see here we have all three types of dimensions in which the flow induced vibrations are there, and we want to apply the scaling law to find out the variation of these with the different dimensions of the velocity in monopole, dipole and the quadrupole. Then this table is clearly showing that when we have the dimension one dimensional feature, the monopole variation, the monopole power with the variation of u is rho 0 CD square u square, and as we are just moving to 2 dimensional and the 3 dimensional, there is a clear impact in the velocity formation, and we have the rho 0 d square u cube, and even the 3D, the scaling law clearly says that our characteristic velocity feature is now variation with u4 by c. And if we are just going to dipole and this quadrupole, then we have a clear variation, like you see here we have in 1D the rho 0 d square u to the power 4 by c. In dipole, in 2D structure, the variation of this wd is rho 0 d square u5 by c square, and if you are going to 3D, then it is u6 by c cube. So, how you see the variations are become so significant and in the nonlinear nature, and that is why you see more and more turbulences are being created in that. And if we are going to the quadrupole, even in the 1D part, we have the clear variation of the characteristic velocity u6 by c cube. In 2D it is u7, and in 3D it is u8 by c5. So, you see here these features are clearly showing that how the sound or vibration fields are being generated under these monopole, dipole and quadrupole when these things are being passing, or when the space is being used, the space region in 1D or 2D or 3 dimensional regions. And we can see that when we are in the worst condition, when we are under the quadrupole and 3 dimensional feature, the power which is being generated there is rho 0 d square u8 by c5, which is of a significant part here. So you see here, when we are going to the basic application there, then we have the whistle sound as we discussed. So in this kind of thing, sometimes the light hill rules are somewhat, you see, not appropriate, because there is a strong interactions are there in between the vibration field and the flow field. And in this you see here, the vertex shadings are being generated around the body of flow field, or we can say at the sharp edge. And if the flow field is not significant in the turbulence part, then the shading is always being a periodic, and which corresponds to a particular dedicated frequency, which is the characterized frequency of the shading, called the shading frequency. And this frequency is proportional to the relevant Strahl frequency like FVS, like we can say omega into FST. And for these cases we can say that the vertex shading frequencies are absolutely coinciding with the resonant frequency of the system and gives us the resonant features of that, the huge amount of excitation. So we can say the alpha FST is nothing but equals to the resonant frequencies, and this condition is coming under the self-excited acoustic oscillation feature. And this condition is really necessary, but sometimes it is not that significant, because you see this is the self-excited system, and we know that a positive feedback can always be there in between the flow field and the vibration fields. And how we can correlate that? Because if like the things are being coming through a self-excitation, sometimes it can lead the system towards the unstable feature also. So when this self-excited system is obtained, the amplitude is certainly growing until it is not approaching up to the nonlinearities and the losses. And this phenomena can generate a very strong tonal or the vibration excitation, and which we are saying that the whistling feature of the system. And this whistling feature of the propagation of the sound or vibration is always nonlinear in its nature. And we can say that there are two ways to eliminate this part, the whistling sound or vibrations. Either we need to put some kind of obstruction in the flow, so that we can straightway reduce the degree of turbulence, we can reduce the effect and by increasing the degree of turbulence. So what will happen in this case, the periodic settling, whatever you see the excitations are there, it simply breaks down, and we have, you see, the two different frequencies are there, not at the resonant conditions. Or else we can modify in the system, like you see, like we can say we can increase the flow velocity, or we just increase some dimensional features, or even we change the material property, so that the resonance will not come into the system, and we can avoid this whistling feature in the system. Because whistling feature is one of the we can say dangerous or drastic feature in the system, through which we can we can have a huge amount of vibration and the sound is. So you can see, you see there are two fall. One, as we discussed, when we are putting some kind of, you see, the obstruction, so that there is a deviation, or we are just changing the material property, or we are just putting some like we can say abrupt change in the dimensional features in that, so that the things are not being coming into the flow field. So you see here, but these two cases are clearly showing that when the things are not being adopted accordingly, the whistling tones are being there. So either the periodic vertex shading is there from the bar of bending vibration, we can say that the self-excitation vibration in the acoustic will be generated. And then you see here, either we are just saying that when the high speed electric train is passing, and the linkage which is extending from the train to any like we can say the electric net, trackside net, is creating this kind of self-excited vibrations by the shading frequency when they are coinciding to that bending resonances. And in the second case, we can even take the periodic vertex shading at the whole, when they are just just passing to the sharp edges of these things, it can straightway go into the resonant conditions in that. And if the shedding frequency is coinciding with this Helmholtz resonances, as I showed in the previous case, certainly we have the resonant condition and the huge amount of vibrations are being generated. Like we know, the simple example is the flow induced visual noise when they are being generated by the Gardner trimmer. And this is basically, you see, we can simply say it is absolutely based on the striking grass, steam and thin branches are there, and when these things are being just going towards the nylon cord, we have a clear huge sound is there, or the vibrations are there at that. Or else even we can say that the wind generated tones, when they are just passing through the high smoke stacks, then certainly we have a clear periodic vertexes are there, and through which the vibrations are being generated. So that is why you see the spiral shaped flanges are being there, which are being wrapped around these smoke sticks, so that whatever the velocities are being passing through, we can at least obstruct or we can disturb these flow, so that the vertex shedding can be disturbed here. So you see here, this is what it is. We have a clear spiral features are there, and these are just to avoid the whistling sound feature in the entire smokestack, so that we can have a clear distribution of those vertex generation features are. So in this lecture, we mainly discussed about the flow field and the vibration field interaction, and how you see the flow induced vibrations are there in that, and then what exactly the basic mechanism by putting the Light-Hill laws, and even you see when we have a clear interaction of the flow field to the surfaces, and how the things are being significant. And also we discussed about that how we can adopt like the different strategy to reduce the whistling feature of the sound and vibrations, because we know that at certain condition the resonances are being occurred, and it is creating the huge amount of damage to the system itself. Now in the next lecture, we are again going to discuss about the vibration generation mechanism, but it is absolutely with the mechanical component like the flexible rotor or misalignment rotors are there. So you see here, we know that the rotor is one of the basic rotating element in those cases, and they can create a huge amount of the sound and vibrations when they are operating at high speed, or when even like during their operations, how the other features are being affected when these propagations are there, because this is a solid media where the propagation is very fast and can damage to the entire system. Thank you.